Hello, and here we are with, you guessed it, more derivatives. And I'm going to be talking about 3.8 in the textbook today. And 3.8 is where the book actually first introduces the log derivative, which is something we've already talked about, and is on the derivative pattern sheet over here. But there is one more thing in 3.8 that I haven't mentioned. But before we do that, I thought it might be fun just to do a couple of these derivatives that are in 3.8, since these are going to be probably the hardest derivatives. And I'm just going to start simple. So 1 over natural log of 3x, and let's just do some derivatives. Just a couple of the harder ones. So first thing I would do with this, just to be as clear as possible, and that is not what I would do, is I would rewrite this in terms of powers. So if we go back to the original problem, we see it's 1 over, and if we put it back into a power form, we can see that the outer function here is a power function. So if we look at this, 3x, that's a power function inside a log function, and all of this is inside this power function. So it's going to be chain rules here. And our first chain rule that we will come across will be this outer power. So we'll take the derivative like we normally would with a power, where the -1 drops down. Subtract 1 from the exponent, so -1 is -2. And that is the first derivative of the chain rules that will happen here. And then the derivative we would have to do next is what's inside the derivative, which is the derivative of the argument. And so that'd be a good first step if you like writing things out. And now we would do this next derivative here. So now our outer function is log, the inner function is the power. And so now we do the derivative of this. And the derivative of log is 1 over the argument. So the derivative of the log here is 1 over the argument. And then we would have to do the one more chain rule on the 3x. So here's our first step. Here's our second step. And now we'll do the last one. And then the derivative of 3x is 3. And there's our final answer. We can clean it up slightly because these 3's will divide out. But that's going to be it. That is our final answer. So we had 2 chain rules there. So let's check out something a little bit harder. Well, x times the quantity log x squared. Check out this derivative. And what should you notice first? Well, we have a product rule here because we have a power function times another power function that has a log in it. So I'll just say it again. This right here is a composite function. It's a log inside a power function. So here's our composite where the chain rule will be. And this is being multiplied by just a power. So we have a product chain rule here. And let's check that out. So actually, I was going to do my way of doing it, which means I don't write stuff out normally. But I do want to write this out, though, very specifically, so people can understand all the steps. So remember, our first step with product rule was to define f and g. So we're saying here f equals x, and then we're saying g equals the composite power there. And then once we specifically state what f and g are, we get those derivatives. And the derivative of x is 1. And the derivative of g is where our chain rule is then. So the outer function here is a power. So the 2 will drop down and subtract 1 from the exponent. So 2 minus 1 is 1. And, of course, normally you don't put a 1 there if it's 1, so I'll just get rid of that. And that is the outer derivative. And now the chain rule says, cool, you did the outer derivative, but now you need to do the inner. You always have to do the derivative of the argument. And so the derivative of log x is 1 over x. And I suppose we could clean this up slightly, because we don't need the parentheses here anymore. And we could put this all into the numerator here. And there's our derivative. And now using the product rule, which I have on the right here, the product rule. So we'll do f g prime plus f prime g. So for our derivative, let me see if I can show that again over here for the product, in case you want to see it right here. We're going to do f g prime plus f prime, which is 1, times g. And that's our answer. And there's only one thing we could, well, there's two things we could do, because these x's here will divide out. And we could get a greatest common factor out of this. Since both terms have a log x, we could factor that out for our final answer. So let's do a couple more. Again, the point here is to show you some of the harder, I'm purposely choosing some of the ones that are be harder or maybe more confusing looking. So here we have the log of log of log. So first off, there's no division here, so there's no quotient rule. Some people do get confused on whether there's a product rule here. But you have to look at this and say, okay, I have a log function in a log function, and this is all in a log function. So these are all composites here, so there's no product rule here either. There's no function times a function. These are all functions within a function, and that is the composite. So there actually is no product rule here. It's all chain rules. So all these are log derivatives, but starting with the outer log, the derivative of log is 1 over the argument. And the argument of the outer log is log of log x. And that would be our first derivative we take here. And then the chain rule says that's great, but now you have to multiply by the derivative of the argument. And so this would be our first step. we did the outer log, which is 1 over argument, and then times the derivative of the argument. That's what the chain rules allows us to do. And so now we have this new derivative we have to take. Again, it's a log in a log. The derivative of log is 1 over argument. So now the argument is just log. So this derivative here is 1 over the argument. And then we have to multiply by the derivative of the remaining argument. And so there's our next step. And then finally, the derivative of log is just 1 over x then. And there's our final answer. So I suppose if you wanted, I mean, there's many ways you could write this. So another thing we could do I'll put some multiplication dots in here to be as clear as possible. We could also write it like that. I know MyMathLab does not like negative exponents for whatever reasons. But this is, I think, actually a better looking answer. But, you know, what's better is subjective. Either way, both of these are 100% correct answers. So here's another one that looks pretty scary. And 2 reasons I want to choose this one. One is because it does look pretty intimidating, but another is because it does have the natural log, and it's pretty common now in calculus to exploit log properties to try to make things simpler. So for instance, with this particular problem, we have the log of a square root. Remember, the square root means raised to a power of a half. So if I want to get rid of the square root, then I can replace that with a power of a half. And with log properties, if we have something that is log x squared, let's say, recall that log properties allow us to take that power and put it in front of the log. And that's extremely useful here, because power of a half means we have a power function here. But if we bring the half down in front of the log, that power function is gone. So it makes things simpler. And this would be a better place to start. Less steps than having to deal with the power function. Just use log properties, bring that half down. So to take the derivative, the derivative of log is 1 over the argument. So there is 1 over the argument, the whole thing that's going into the log function. And then the chain rule says, take the derivative of that. So again, the first step here was just to bring the half down, use some log properties. And a second step then is actually doing the derivative. So we have our constant, which just will remain out front there. Then the first function we encounter is log. The derivative of a log is 1 over the argument. So that was our next piece here. And then the chain rule says, okay, now multiply that by the derivative of the argument. And now we'll do that. So this derivative here, notice there is division in it. So let's deal with this separately, because this is where the quotient rule is. And so we'll call this then our f and g. So that means we're explicitly defining f to equal the top function, power function there, and the bottom one so there's our f and g for the quotient rule. Once we have that, we'll take those derivatives and notice for the derivative of f, the 5 drops down. Subtract 1 from the exponent. And now the chain rule says take the derivative of the argument. So here's the argument. And this derivative is 1. So here's a case where the chain rule multiplies by 1, so there's no change there. And same with g prime. The exponent drops down, subtract 1 from the exponent, multiply by the derivative of the argument, and this derivative is 1. So there is our two derivatives for f and g that we can now stick into the quotient. So finally, we'll have for this derivative, looking at, let's see if I can squeeze all this in. So we got our functions here, our quotient rule over here. And so we have f prime. Times g. Minus f g prime. All divided by g squared. Now this is raised to the 20, and we're squaring it. So an exponent raised to an exponent means you multiply. And there it is. Not pretty looking. But here is our derivative then for x plus 1 to the 5th over x plus 2 to the 20th. And now we can go back to our problem here. I'm just going to copy this step from where we left off. Here's that step where we left off. Here's the derivative that we just figured out. So that means all of this will get pasted right here where we just figured out this derivative. There it is. So if we wanted to see what we can do to clean this up, this 1 divided by this, we can multiply by the reciprocal on that. So we could bring that, x plus 2 up. There we go. So multiply by the reciprocal, we'll flip that. We get some x plus 2. Well, let me leave that as a step. So all I did was Whoops. Let me copy that again there. So all I did was flip this. And now these x plus 2's, we have some of those that'll cancel. So we have 20 of these and 40 of these. So 20 will go away. And I'll leave that as a step. And what else could we do? Certainly not going to distribute all that out. This 20, pretty common to move constants in front like that. They all have x plus 1 in common and an x plus 2. So let's see here. There's 4 x plus 1's here and 5 over here, so we can pull out 4 of these. And we have 19 x plus 2's and 20 x plus 2's, so we can pull out 19 of them. And this is actually cleaning up pretty nice. Take this 2. Leave that as a step. So just all I did was greatest common factor there. And we could clean this up in here. So we'd have 5x plus 10. And minus 20x minus 20. And we'd have a 5x minus 20x get us a minus 15x. And 10 minus 20 to get us a minus 10. Which reveals another greatest common factor here of 5. A minus 5 would actually be pretty common to pull out here, because they both have a minus sign as well. And there it is. The final cleaned up answer. It's about the best it's going to look. Oh, wait a minute. There's more x plus 2's that cancel here. Actually, let me leave that as a step. And x plus 1's. Wow, all sorts of stuff. So we got 19 of these. We'll take out 19 of these to leave 1 left down here. We got 4 of these. So I'll take out 4 of these to leave 1 of these left. And that will do it. So actually, that cleaned up pretty nice. Now I'm just really being nitpicky right here. And there is the final answer. So let's check out actually one more here. This is the last problem in the book, because I want you to get an idea of what is the maximum difficulty here that the book has to offer, and then your homework as well, because it's all based on the book. So here's number 88, and let's check it out. Something else I do want to say, that as you watch me write this out, if you have your own strategy for doing this, I highly encourage you to go with what you want to do. That I do it this way for teaching purposes, to try to make it as clear as possible. But if you have your own way for doing this, hey, as long as you're doing the math right, that's what matters. So if you do have your own method here, I strongly encourage you to do you. So let's look at this and see what we have. We have a function here, a power function, multiplied by a log function. So that means product rule. And then we see inside the log function is another function. So this is a composite here. And we see there's an exponential inside the log. And inside the exponential is a trig function. So don't let this log3 fool you too much there. That's just a number. It's just a constant. And we can just treat it simply because it's a constant. So the first thing we're going to do then is product rule, because we have a function times a function. And then once we identify that, we will explicitly define then f and g. So we're going to say f is a nice simple x there. G is where all the fun is, though. And, well, that's just a lot of work even to write in. So I'm actually going to switch this around to make it a little bit less confusing, because you'd normally put a constant first. And that's our g function. And once we explicitly define f and g, we will take their derivatives. And the derivative of f is x. Derivative of x is 1. And the derivative of g is where we will have our chain rule then. So first off, the derivative of a log is 1 over the argument. So here's the argument. I'm just going to write this out over here for a moment. Oops. So the derivative of log is 1 over the argument. In this case, however, we do have a log base 3. And so pretty easy to forget that that log base 3 will cause a natural log then to be in the denominator there. So if we look over to the right for logarithm functions, the derivative of log is 1 over the argument. And there's also this natural log of the base that's always in the denominator. It's just sometimes when you have log e, that's 1. But in this case, we don't have base e. So this is the derivative of log. And then next, we would do the chain rule. Oops. And multiply by the derivative of the argument. So here's what our derivative looks like so far. Did our one chain rule. We did 1 over argument for log. Multiply by the derivative of the argument. And so the derivative of e is itself. So I'm just going to paste that in there. And then the chain rule says, well, you still got to multiply by the derivative of the argument. And now the argument is this natural log 3 sine x. And here, natural log 3 is just a constant. And we can pull that outside the derivative. And so here's where we're at now for our derivative. And now the derivative of sine is cosine. And I'm just going to clean this up a little bit. Take this log 3, stick it up here, because then we can see these log 3's cancel. And if we do that, we notice these e's cancel. Well, that's pretty nifty. And that all comes down to cosine. I had no idea that would happen. Well, that's pretty fun. All of a sudden, what I thought was going to be a fairly challenging problem has turned out to be pretty simple with that nice chain rule happening there. And now we just go on to the product rule. And let me show our functions here. And the product rule on the right side over here. So we have F times G. And I'm just going to copy that. F times G prime, actually. Whoops. I'm so anxious to copy and paste stuff. It's actually F G prime. So there's F G prime plus F prime, which is 1. And now here comes the G I can paste in there. And that's our answer. Nothing to simplify there. So there is actually one last thing I want to say about this problem in my just double checking myself to make sure all that cancellation stuff really happened, is if we look at G here, we can actually use a log property on this. So if you remember the change in base that you can do with log, this is something we can do, what that formula would look like. And in this case, we're in base 3. And that's what our change of base would look like. And so what does that mean? Well, that means we could take our function and instead of log 3, we can see log 3 is log x over log 3, natural log in this case. So that means this right here would be natural log of all that, all over natural log of 3. So that's just using log properties for G right here before we get to derivative. Use a log property. And then we can continue on with that. Because now we have log of E. And if you further remember your log properties and exponential functions, the natural log of E is just the exponent then. And then here's our denominator. And we see those natural logs of 3's divide out, and we're just left with sine. And the derivative of sine is our cosine we got. So just showing, again, some log properties, and they are very useful in calculus. And this is a great example of if I would have done log properties first, this all reduces just to the derivative of sine. So there's a couple examples. In the next video, I'll talk about what's new in 3.8.